everyone, this is a video for class 29 of PH 125, and today we're going to be continuing to talk about waves. Specifically, today we're going to be focusing on the interference of waves and then also on standing waves. Okay, let's start with a quick review of things that we've learned about waves so far. So remember, waves are classified by how they make the medium that they're propagating through move. And so when we talk about transverse waves, remember a transverse wave causes the medium that it's propagating through to oscillate in a direction that's perpendicular to the direction of propagation of the wave. A longitudinal wave causes the medium that it's propagating through to oscillate in a direction that's parallel to the direction of propagation of the wave. A classic example of a transverse wave is a wave on a string, and a classic example of a longitudinal wave is sound. Then remember that whether the wave is transverse or longitudinal, we know that the speed of a wave is given by its frequency multiplied by its wavelength. So in other words, v is equal to f times lambda. Specifically, if we're talking about a wave on a string, we know that that speed is also equal to the square root of the tension in the string divided by the mass density of the string, mu. Okay, and last class we also talked about the Doppler effect. The Doppler effect can be observed for any type of wave, but we specifically talked about the Doppler effect for sound waves. Okay, and so the Doppler effect tells us that the observed frequency is going to be related to the source frequency, but they won't be the same if there's relative motion between the source and the observer. Okay, so specifically here what we learned is that the observed frequency f prime is proportional to the source frequency f, and that proportionality constant is going to depend on the speed of the observer, uo, the speed of the source of the sound, us, and then also the speed of sound in air, assuming that the observer and the source are both in air. Okay, and so that's what we call v. All right, that proportionality constant between f prime and f also depends on the relative motion between the observer and the source. So in other words, is the source moving towards the observer? Is the observer moving towards the source? And that dependence comes into play in how we choose the signs that are appropriate for our given situation inside this Doppler effect equation. So specifically, we remember that top is toward. So in other words, if the observer is moving toward the source, you pick the top sign in the numerator, which is the plus sign. If the source is moving towards the observer, you pick the top sign in the denominator, which is the minus sign. Okay, and last class we also talked about intensity. Remember, in general, intensity is power per area. Power is energy per time. So we can also think about intensity as energy per time per area. All right, and then specifically, if you have a point source of waves, like you will for most sources of sound, then it turns out that those waves will spread out spherically from the source. So what that means is that if you are at a distance r from that point source, so the source that's creating these spherical wave fronts, then the intensity at that particular location defined by r is going to be equal to the power of the source of the sound divided by 4 pi r squared, where 4 pi r squared is like the surface area of the spherical wavefront at the location r, which is at a distance r from the point source. Okay, and then remember that intensity is really related to the loudness of the sound that you perceive. However, the human perception of loudness is really logarithmic in intensity. And so what that means is that it's convenient to define intensity levels and the decibel scale to describe the loudness perceived by the human ear. Okay, and so the intensity level, which is measured in decibels, is defined to be 10 times the log base 10 of the intensity of the sound that you're interested in, divided by I naught, where I naught, remember, is the threshold of hearing. It's 10 raised to the minus 12 watts per meter squared. All right, and then last class, we also started talking about superposition and interference, and that's where we're going to pick up for today. Okay, so the basic idea of superposition of waves is that waves at the same location at the same time will add. So what that means is that the overall or observed amplitude of the resulting wave is going to be the algebraic sum of the amplitudes of the individual waves at each point in space and each point in time. Okay, so let's go ahead and look at some examples here. So in this first example, we have a red wave and a blue wave that we're going to assume are at the same point in space at the same point in time. Here you can see that the red wave and the blue wave, they have the same overall amplitude, and you can see that they're at the same height at each moment in time. And so what that means is that here you can see the red wave is at a peak when the blue wave is at a peak, the red wave is at a trough when the blue wave is at a trough, and etc. Okay, and so then if we were to think about the interference of those two waves, they would just add together the heights at each individual point in time and space to get the resulting wave. And so that would give us like this purple wave shown below. And here you can see that at each point in time and space, that wave is at twice the original height of one of the individual waves. So in other words, we've just added together the heights of those two individual waves at each point in space. And so then the overall amplitude of this wave is going to be twice the amplitude of the individual waves. Okay, and this is an example of what we call constructive interference, because here you can see that the waves add together to cause a larger height at each location in space and time. All right, now let's look at a second example. Again, we have our red wave and our blue wave, which have the same amplitudes. However, now they're shifted relative to each other, so that the red wave is at a peak when the blue wave is at a trough, the blue wave is at a peak when the red wave is at a trough. And so then if these two waves were at the same point in space at the same point in time, to get the overall resulting wave, you would just add the amplitudes at each location in space and time together. And here you would see that those waves would exactly cancel out. So the peak would add to the trough to give you a 0 amplitude, and similarly the trough would add to the peak to give you 0 amplitude over here. And so this resulting wave is going to have a smaller amplitude. In this specific case, it has 0 amplitude throughout space and time. Okay, and so then this is an example of what we call destructive interference. Destructive interference is any time that waves add together to give you a resulting wave with a smaller amplitude or a smaller displacement. Okay, and so now we want to think about what is the condition that we need to get constructive interference versus what is the condition that we need to get destructive interference when we have two waves in the same place at the same time. And so really the difference between these two cases is what we call the relative phase between the two waves. Okay, and so then we want to know, what is the phase of a wave? Well, really the phase tells us about what point we are at in a waveform at a given moment in time. And so in other words, is that waveform, is it at a peak? Is it at a trough? Is it crossing 0? Those types of things all tell us about the phase of the wave. And so mathematically then we can measure the phase of a wave in terms of either angle, so it could be in terms of radians or degrees, or you could measure it in terms of fractions of a wavelength. So here when we think about fractions of a wavelength, remember that sine and cosine functions have wavelengths of 2 pi radians, or in other words 360 degrees. So one full cycle of this sine function that's shown up above here is going to correspond to 360 degrees or 2 pi radians. And so then we can think about moving a particular waveform, shifting it by some phase, by thinking about it in terms of moving it by some amount of degrees along this x-axis here, or by shifting it in terms of a fraction of a wavelength. So then remember that on the previous slide, when we had two waves that were both peaks at the same time and both troughs at the same time, they added together constructively. When instead we had one wave that was at a peak and the other wave was at a trough, then remember they added together destructively. And so what that means is that the relative phase shift between different waves that are adding together, the waves that are interfering, tell us about whether they will interfere constructively or destructively. Okay, and so let's talk about the first example where we had two waves that were both peaks at the same time, and that gave us constructive interference. Okay, so it turns out that if you have two waves that are both peaks at the same time, there are many ways that you could get that to happen. So it could happen if they were both at exactly the same phase at the same time. So we would call that in phase. But because the waves repeat themselves over the course of one full wavelength, this could also happen if one wave was shifted by one full wavelength relative to the other. So in other words, if you were to think about this red curve here, if you were to think about shifting it so that this peak was moved one full wavelength to the right, then you would have this peak over here at the other peak. And so then that wave would look exactly like if it wasn't shifted by one full wavelength. And so you would still have completely in phase waves. Okay, this would happen even if you shifted this red wave by 2 wavelengths instead of 1, or 3 instead of 1, or if you shifted it backwards by 1 wavelength. Okay, and so the overall result here is that if your phases of your two waves differ by some integer multiple m multiplied by the wavelength, so in other words, m could be equal to 0, plus or minus 1, plus or minus 2. So if your phase shift is m times lambda, then you're going to get completely constructive interference of your two waves. Then remembering that one full wavelength is equal to 2 pi radians or 360 degrees, that means that you could also have a difference in phase of 0 degrees, 360 degrees, or any integer multiple of 360 degrees. And you would still get completely in-phase waves, which would lead to completely constructive interference of those two waves if they were to reach the same point in space at the same moment in time. Okay, now let's look at our second example, which remember was the case where we had one wave that was at a peak when the other wave was at a trough. This is what we refer to as waves that are completely out of phase. So in other words, one wave is at a peak and the other wave is at a trough. So remember that one full wavelength would correspond to the peak-to-peak distance. So let's look at this red wave here. So one full wavelength would be from the red peak to the next red peak. Then if you think about it, going from peak to trough, well, that would be half a wavelength. So that would be like lambda divided by 2. And so then to get waves that look like this completely out of phase, like we have here where the one wave is at a peak where the other is at a trough, that means that the shift between them, the phase shift between them, it's equal to lambda over 2, half a wavelength. This could also occur if the shift was 3 lambda over 2. So in other words, one full wavelength plus another half. Or you could have 2 full wavelengths plus another half. And then you would still have your waves so that one was at a peak when the other was at a trough. Okay, and so mathematically what that means is that we could say that the phase shift between the two waves is equal to m plus 1/2 times lambda, where just like in the previous case, m could be 0, it could be plus or minus 1, plus or minus 2. Any integer value will work for m there. All right, then in terms of degrees, this would correspond to 180 degrees phase shift, or you could think about adding 360 degrees to 180 degrees. Okay, so that would give you 540 degrees. Or you could have 2 factors of 360 degrees added to 180 degrees. So these are completely equivalent ways to think about how you could get completely out of phase waves, which would lead to completely destructive interference. So for example, here, if you were to think about adding the heights of the red and blue waves at each point in space, you would see you get exact cancellation of those two waves at every point in space. So that's our completely destructive interference example. Okay, let's do some practice here. So consider the red and blue waves that are shown and determine how much they are out of phase relative to each other. Okay, so to think about the relative phase shift between these two waves, it's easiest for me to think about the distance between two peaks. So I'm just going to start by picking out a peak on the red wave and a peak on the blue wave to compare. All right, so I've denoted the 2 points that I want to compare with these 2 yellow stars. All right, and then we can think about the phase shift either in terms of the angular displacement between the red peak and the blue peak, or in terms of the fraction of a wavelength that corresponds to the distance between the red peak and the blue peak. All right, so here, since our answers are in terms of angles, let's think in terms of angles. And so then remember that one full wavelength is equal to 360 degrees. So here you can see that one full wavelength would be 360 degrees from this red peak to the next red peak. So that's too far compared to the distance between the red peak and the blue peak that I have chosen here. All right, so our phase shift is going to be something less than 360 degrees. So let's try half a wavelength, or in other words, 180 degrees. Then remember, half a wavelength or 180 degrees, it corresponds to the distance between a peak and a trough. And so here you can see that the trough of the red wave lines up exactly with the peak of the blue wave. Okay, and so then I would say that the phase shift between these two waves is 180 degrees. Okay, and so then I would go ahead and pick answer A here. Let's do another practice problem here. So we have two waves with equal wavelength lambda that are emitted from two in-phase sources. So that means that both waves are going to be emitted at peaks at the same time, and both are going to be emitted at troughs at the same time. All right, so first of all, let's just think about wave 1, which is emitted from source number 1. So wave 1 travels a distance d1 of 2 wavelengths to get to some point of interest P. Ultimately here we want to determine whether or not the two waves are going to interfere constructively or destructively at point P. So first of all, we just want to think about if wave 1 was at a peak when it was emitted from the source, what is its height going to be when it reaches point P? Okay, so to answer this question, I would think about sketching it out. So first of all, we know that the wave is emitted at a peak. So I would start at a peak and draw in a little dot that corresponds to the source location. So my wave is at a peak at this source. All right, then we know that the wave travels a distance of 2 wavelengths to get to our point P. And so that means that if my wave starts at a peak, then it's going to go through 1 peak, 2 peaks to get to point P, because that would correspond to 2 full wavelengths. Okay, so it travels a distance of 2 lambda, and that means that when it arrives at point P, since it started at a peak when it was at the source, it's going to be at another peak when it gets to point P. Okay, so I would go ahead and pick answer A here. The wave is going to be at a peak when it reaches point P. All right, now let's think about wave number 2. So wave number 2 is also going to be emitted at a peak at the source, and then it travels a distance of d2 that's equal to 2.5 wavelengths to get to point P. And now we want to know what is the height of wave 2 when it reaches point P. Okay, so once again, I would think about sketching this out. Once again, at the source, this wave starts at a peak. So I would draw a peak right in at the source. Then this wave travels a distance of 2.5 wavelengths to get to point P. So that means you need to go through 1 peak, 2 peaks, and then half a wave means that it goes from peak to trough. So then it would end up at a trough at point P. Okay, and so then I would go ahead and pick answer B. When this wave gets to point P, it's going to be at a trough, or in other words, it's going to be at a height of negative A, negative the amplitude of the wave. Okay, and then here's our end goal for this question is to think about when these two waves reach point P, will they interfere constructively or destructively? Okay, so here I would want to compare the two sketches that we made on the previous slides. So remember, wave 1 traveled 2 wavelengths to get to point P. It started at a peak, and so then it was at a peak when it got to point P. Then wave number 2 traveled through 2.5 wavelengths to get to point P, and so then since it started at a peak at the source, it ended at a trough when it got to point P. And so then at point P, you can see that wave number 1 is at a peak, wave number 2 is at a trough, and so when they interfere, remember that means that you want to add the amplitudes of the two waves at that particular location. And so that means you're adding a peak from wave 1 to a trough from wave 2, and so then that means that they will interfere destructively here. So I would pick answer B. Okay, so now we really just want to generalize the results of that last problem. So that means that our goal is going to be to determine whether interference of two waves at some particular location, let's call it P, is constructive or destructive. So if we have a problem where that's our goal, what we're going to need to do is to determine whether the two waves are going to be in phase or out of phase when they reach some particular point of interest. Okay, so in these types of problems, you're often told that the sources are in phase. So in other words, you're going to have two waves that are created by two different sources. And oftentimes in this problem, you'll be told that they're in phase, which means that the two waves are going to be emitted at the same frequency, and that those two sources of the waves are both going to be emitting peaks at the same time and troughs at the same time. Okay, so that's what we mean when we say that the two sources are in phase. Alternatively, you could have some problems where you're told that the sources are 180 degrees out of phase. In that case, again, the two sources are going to be assumed to have the same frequency so that your waves have the same wavelength. But what that means when we say that that's 180 degrees out of phase is that when one source is emitting a peak, the other wave is going to be emitting a trough. All right, so let's just look at an example here where we have two sources that are in phase. This is going to be the most common example that you'll see. So if you have two sources that are in phase, then you know that the two waves are going to start off with the same phase. So they're both going to be peaks at the same time, they're both going to be troughs at the same time. And so then the difference between the phase of the two waves when they get to the point of interest is going to correspond to the difference in the distances that the two waves have to travel to get to that point of interest. Okay, and so here let's think about the first case where we do get constructive interference at our point of interest, which once again I'm calling P. So if we want that to happen, then that means that we want the relative phase shift between our two waves when they get to point P to be equal to some integer multiple of the wavelength. Okay, remember that was our condition for constructive interference, so that our waves end up being in phase when they get to our point of interest P. And so how can we have that happen? Well, it's going to be related to the relative distances traveled between the two waves, just like in the last example. And so then if the difference in the distances traveled by the two waves is equal to some integer multiple of the wavelength, that's going to correspond to two waves arriving at our point of interest in phase, and so that would correspond to constructive interference of those two waves at our point of interest. So in other words, what we want is delta, which is the difference between the distance traveled by wave 2 and the distance traveled by wave 1, to be equal to some integer multiple of the wavelength, and that will give us constructive interference at point P when we start out with two wave sources that are in phase. If instead we want to get destructive interference at point P, then what we need, remember, is that our waves arrive so that one is at a peak when the other one is at a trough. In other words, we need our waves to arrive 180 degrees out of phase from one another. So remember, the condition for our waves being 180 degrees out of phase from each other was that they were shifted relative to each other by some integer number plus 1/2 of a wavelength. Okay, and so then the condition for destructive interference at point P is going to be if the difference in the distances traveled by our two waves is equal to some integer plus 1/2 multiplied by a wavelength. Okay, and so that was the case in the last example. One wave traveled a distance of 2 wavelengths, the other one traveled a distance of 2.5 wavelengths, and so then the difference between the distances traveled by those two waves was 2.5 wavelengths minus 2 wavelengths, which was equal to half a wavelength. And so that's why we got destructive interference in that last example, and this will be true in general for giving us destructive interference at a particular point of interest. Okay, and so these examples here, these are specific to in-phase sources, so these equations are specific to in-phase sources. If instead you have out-of-phase sources, actually these two equations would be switched, because then you have wave 1 starting at a peak when wave 2 starts at a trough. Okay, so we're going to do a lot of practice with this in class, and actually we're going to revisit this topic of interference and superposition next semester. But for now, let's talk about a special type of interference, which leads to something called a standing wave. So a standing wave is really a wave that oscillates in time, but it appears to be fixed in position. And this occurs when you have a wave on a string or in a pipe that interferes with its own reflection. So let's start by thinking about a standing wave on a string. And so to get a standing wave on a string, you have to have a string that's tied down at two ends. So in other words, you have two fixed ends on your string. And then remember that when you have a fixed end, the reflection of the wave on a string is going to be inverted. All right, and so what ends up happening then is that you get this special interference between a wave and its reflection that causes certain points on the string to appear stationary because you constantly have completely destructive interference at those particular points on the string. So that's why you end up getting these stationary points, and we call them nodes. Okay, and so then you get these nodes which stay fixed in space, and they are constantly zero amplitude. Then in between the nodes, you get oscillations of the string. So specifically, the places where you get maximum oscillation, that's what we refer to as the antinode. All right, and then it turns out that there are conditions that are required to give you standing waves on a string. And so specifically, you always have to have nodes at the places where the string is tied down. So in other words, the two ends of the string that are tied down always have to correspond to nodes. Then you could have varying numbers of nodes and antinodes in between those two fixed ends. So in this top figure, you can see that the only nodes are at the two fixed ends of the string. There are no additional nodes, and this gives us just one antinode in the middle of the string. Alternatively, we could have a case where we have one additional node between our two fixed ends. This would give us two antinodes for our string. So in other words, as this string oscillates up and down, you would see like two oscillating humps, and then you would have a fixed point right in the middle of the string, as well as two fixed points right at the ends of the string where it gets tied down. And we could keep adding nodes in between our two fixed ends, so you could have two nodes in between the two fixed ends, which would give you a total of 3 antinodes, 3 oscillating humps for your wave on a string. All right, and so then it turns out that there's a well-determined relationship between the wavelengths, or in other words, the frequencies of these standing waves that you can get on a string. So let's start by thinking about the wavelength of the wave that's required to give us this top case where we just have one antinode between our two nodes, so between our two fixed ends of the string. So here notice that the distance between the two fixed ends of the string, we're calling it L. And so then we can relate the wavelength that's required for this condition where we just have one antinode to the length between the two fixed ends, L. Specifically here, if you think about this wave, it's just like one peak or one trough. And so it's not the full wavelength of the wave, it's really half a wavelength of the wave in between our two fixed ends. And so what that means is that the distance L between our two fixed ends, that corresponds to half a wavelength. So let's say that L in this case is equal to lambda 1 divided by 2, where we're calling it lambda 1 because it's the wavelength of what we call the first harmonic. It's the case where we just have one antinode between our two fixed ends. Then we can go ahead and rearrange and solve for lambda 1, and we can see that lambda 1 is just going to be equal to 2 times the distance between the two nodes. Okay, now let's go ahead and think about our second case down here. Here you can see that the string has one full wavelength in between the two fixed ends. So that means that one full wavelength is going to be equal to L, the distance between our two fixed ends. So in this case, let's say that L is equal to lambda 2, where lambda 2 is the wavelength of the second harmonic. The second harmonic corresponds to the case where we have two antinodes between our two fixed ends. All right, and so then you can see that lambda 2 is just equal to L. All right, let's do our third case down here, and then we'll be able to pick out a pattern. So in this case, you can see that there's one full wavelength plus another half a wavelength in between our two fixed ends. And so then I would say that the distance L is going to correspond to 3 halves of this wavelength. So it'd be 3 halves of lambda 3, where 3 corresponds to the third harmonic. In other words, there are 3 antinodes between our two fixed ends. Okay, and so then we can see that lambda 3 is going to be equal to 2L divided by 3. Okay, and so then comparing these relationships, we can see that in general for the nth harmonic, which would be when you have n antinodes between your two fixed ends of your wave on a string, you get 2L divided by n. Okay, so the wavelength when you have the nth harmonic is going to be 2L, 2 times the length between your fixed ends, divided by n, the number of antinodes that you have on your wave on a string. Okay, you can also rewrite this as lambda n is equal to lambda 1 divided by n, where lambda 1, remember, is this wavelength for our top case, which we said was our fundamental harmonic or our first harmonic, and so that was the case where lambda 1 was equal to 2L. All right, then remember that the speed of the wave on a string is equal to frequency times wavelength, and so what that means is that we could also think about the frequencies of these different harmonics. So in other words, the frequency is just going to be the speed of the wave on the string divided by the wavelength. So here, if we wanted to know the frequency of the nth harmonic, we would just need to divide the speed of the wave on the string, which we know is going to be the square root of the tension in the string divided by the mass density of the string. So that speed divided by the wavelength of the nth harmonic, which is given up above. Okay, and so then we would get that Fn is equal to n times the speed of the wave on the string divided by 2L. Alternatively, then we could define the fundamental frequency, which is the frequency of the first harmonic, to be equal to the speed of the wave on the string divided by the wavelength of the first harmonic, which remember was 2L. So if we define F1 to be equal to V divided by 2L, then we can see that the frequency of the nth harmonic is going to be equal to n times the fundamental frequency. Okay, let's do a little bit of practice here. So which of the drawings correctly represents the third harmonic for a wave on the string? Okay, so remember that for a wave on a string, the harmonic is given by the number of antinodes that you can see. And so here the antinodes, remember that's like the number of humps. And so in this first case, there's one hump, there's one antinode, and so this would be the first harmonic or the fundamental harmonic. This second case has 2 antinodes, and so that would correspond to the second harmonic. Case C here has 3 antinodes, and so that would be the third harmonic, and so that's going to be the one we're looking for. So I would pick case 3. Just for completeness, case 4 has 4 antinodes, and so that would be the fourth harmonic. Okay, so like I mentioned, case C would be our answer of choice here. All right, so I mentioned that standing waves can occur both on a string or in a pipe, and so now let's talk about standing waves in a pipe. Okay, so for standing waves in a pipe, it turns out that we can talk about 2 different types of pipe. So we can talk about a pipe that has one open end and one closed end, or we could talk about a pipe that has 2 open ends. So let's start by talking about a pipe that has one open end and one closed end. Okay, and so then when we talk about the standing wave that's created in a pipe, it's going to be due to reflection of the wave at the 2 ends of the pipe and then the corresponding interference of that reflected wave with the original wave. Okay, and so here we can see that if we have a closed end, we're going to get fixed end reflection at that closed end. When we have an open end, we get free end reflection of the wave. And so the fixed end reflection, that means that we're going to have inversion of the wave. The free end reflection means that we don't get inversion of the wave. Okay, and so what that means for us is that we need to have the fixed end correspond to a node, and the open end needs to correspond to an antinode to get a standing wave in a pipe that has one end closed and one end open. Okay, and so then the fundamental frequency or fundamental wavelength for a standing wave in this pipe, which has length L, is going to correspond to the case where you have a node at the fixed end and then you have an antinode at the free end and you have nothing in between. Okay, and so then if we want to think about what is the wavelength of a wave that fits in the pipe this way, well, here you're starting at like the zero crossing of the wave and you come up to the peak. So then to get one full wavelength in here, you would have to come back down to a zero crossing, go down to a trough, and come back up to a zero crossing. And so what that means is that the amount of wave that fits in the pipe in this way is going to correspond to 1/4 of the full wavelength of the wave. Okay, and so then what that means is that L, which is the total length of the pipe, is going to be equal to 1/4 of the fundamental wavelength, which we're going to call lambda 1. All right, so then we can rearrange for lambda 1. Lambda 1 is going to be equal to 4 times L. All right, so that's what we call then the fundamental wavelength, or in other words, the first harmonic wavelength for our standing wave in a pipe where one end is closed and the other end is open. All right, so what's the next way that we could get one node at the fixed end, at the closed end of the pipe, and one antinode at the free end or the open end of the pipe? So the next way that we could get that to happen would be if we snuck in one extra antinode and one extra node in between. Okay, and so then you can see here that the wavelength of the wave that fits in the pipe that way, it's really going to be like 3/4 of the wave that fits in the pipe. So here, if you think about it, we have the zero crossing, there's a trough, we come through zero, we come up to a peak, and so then the full wave would come back to a zero crossing here. And so only 3/4 of the wave fits in the pipe. And so then I would say that in this case, L is going to be equal to 3/4 of this wavelength, which I'm going to call lambda 3. Okay, and so then you can see that lambda 3, which is the wavelength of the third harmonic, is going to be 4L divided by 3. All right, the next harmonic that we could get would be if we snuck in another antinode and node in between our fixed and free ends. And so then we would get a node, an antinode, a node, antinode, node, antinode. All right, and so then in this case, you can see we have one full wavelength that fits in the pipe plus another 1/4. So in other words, that's like 5/4 of the wavelength that fits in the pipe. And so then you would have L equal to 5/4 of the wavelength in this case, which I'm going to call lambda 5. It's the wavelength of the fifth harmonic. And so then you can see that lambda 5 is going to be equal to 4L divided by 5. Okay, and so now we can see a pattern. So in general here, when we have a pipe that has one end closed and one end open, the wavelength of the nth harmonic is going to be 4L divided by n, where n can only take on odd values in this case. So it can only be 1, 3, 5, any odd number. All right, now let's go ahead and talk about what happens when we have a pipe that's open at both ends. So in this case, then we're going to have free reflection at both of the open ends. And so then both open ends have to correspond to antinodes if you want to get a standing wave in a pipe that's open at both ends. Okay, and so how can we get a wave that fits in the pipe so that it has antinodes at both ends? Well, the longest wavelength wave that we could get in there so that it has antinodes at both ends is going to correspond to our fundamental frequency again, or our first harmonic. And so in this case, you can see that we start at an antinode, we start at a peak, we go through a zero crossing, and we come down to a trough. And so that's going to correspond to half a wavelength that fits inside the pipe. So in this case, I would say that L is going to be equal to lambda 1 divided by 2, or in other words, lambda 1, our fundamental wavelength, is going to be 2L. All right, then in our next case, how can we get another wave that fits in here so that we have antinodes at both ends? Well, if you look at this case, then we could imagine sneaking in one more antinode in between. And so in other words, here we would have an antinode. So say we start at a trough, we go through this zero crossing up to a peak, so that's half a wavelength, and then we go through the node back down to a trough. And so here you can see then that that's going to fit one full wavelength inside the pipe. So in this case, we would have L equal to one full wavelength, so I'll call that the wavelength of the second harmonic, lambda 2. All right, next way that we could end up getting antinodes at both ends of the open pipe would be to include two more antinodes in between our two end antinodes. Okay, so let's see how many wavelengths this corresponds to. So here we start at a peak down here, we go through a zero crossing down to a trough, through a zero crossing back up to a peak. So that's one full wavelength, and then we go through a zero crossing down to a trough. And so that's an additional half a wavelength. So here we get 1.5 wavelengths, or in other words, 3/2 of a wavelength. Okay, and so then we get L equal to 3/2 of a wavelength. I'll call it the wavelength of the third harmonic, lambda 3. And so then you can see here that we get lambda 3 is equal to 2L divided by 3. Okay, and so then you can see that this pipe that's open at both ends looks very similar to the case where we had a wave on a string. In this case, the wavelength of the nth harmonic is going to be equal to 2L divided by n. In this case, n is the number of nodes in between the open-ended antinodes. So for the wave on a string, you want to count antinodes to count the harmonics. For the pipe, you want to count nodes to count harmonics. Okay, and so then just a kind of fun side note here, if you've ever blown across the top of a pop bottle or run your finger around a wine glass, you've actually already played with standing waves in a pipe, and that would be the case where you have one end open and one end closed. Okay, and so then you may have noticed that if you take a sip of what's inside, then you can change the frequency or the pitch of the sound that you hear. And so that's really because you're changing the length of the pipe, and so then you change the fundamental frequency that's being played, or the fundamental frequency of the standing waves inside the pipe. So just a little bit of fun there. All right, let's do one more practice problem. So we have an air-filled pipe that is closed on one end and it's 1 meter long, and we want to know what is the fundamental wavelength of that pipe. Okay, so for this one, I always like to draw pictures. For these, I have a hard time just remembering the formulas. I really like to draw a picture. So for an air-filled pipe that's closed on one end, remember you need a node at the closed end and an antinode at the open end. And so then the fundamental wavelength is going to correspond to the wave that just has that one fixed node and then the one antinode at the open end. Okay, and so I like to sketch it out here. I've drawn in my wave here into the pipe, which is a length of 1 meter. All right, and then I can see that that wave inside the pipe, it's going to correspond to 1/4 of the total wave. And so in other words, L corresponds to 1/4 of the total wavelength of that wave. And so then I can rearrange and solve for the wavelength of the wave. So the wavelength of the wave is going to be 4L. L is 1 meter, and so the wavelength of that wave is 4 meters. Okay, that's really it for today, and that actually wraps up our chapter on waves. We'll be doing lots of practice in class, and I will see you guys then.